We will start our discussion of the Nusselt number correlations for free convection with flows over surfaces. For flows over isothermal vertical plates, such as this, the characteristic length that we must consider is the length of the plate L. Under this case, we can use the Churchill and Chu correlation to compute for the Nusselt number for any value of the Rayleigh number. However, please keep in mind that for laminar flows, in which the computed Rayleigh number is less than or equal to 10 raised to 9, more accurate Nusselt number correlation exists. Therefore, we must use this instead for this range of the Nusselt or of the Rayleigh number. For vertical cylinders having a diameter of d and that are oriented in this way relative to the fluid flow, the characteristic length that we must use in solving for the Rayleigh number is the length of the cylinder. Correlations for vertical cylinders differ depending on whether the cylinder can be considered a wide vertical cylinder or a slender vertical cylinder. A cylinder can be considered wide if its diameter exceeds this ratio. In this case, we can simply compute for the Nusselt number using the correlations for isothermal vertical plate. On the other hand, a cylinder can be considered slender if its diameter is less than this ratio. In this case, we can use the Sebezier correlation to compute for the Nusselt number. Take note that nu sub Fp at the denominator on the left side of the equation corresponds to the Nusselt number of an equivalent vertical plate that has a length which is equal to the length of the vertical cylinder under consideration. For inclined plates, we must consider two cases when evaluating the Nusselt number. First is when a cold plate is placed in a hot environment, and second is when a hot plate is placed in a cold environment. Both plates are inclined at an angle of theta from the vertical axis. Now let us see how the fluid surrounding these surfaces moves in each case. When a cold inclined plate is placed in a hot environment, the air at the upper surface of this plate moves towards the plate first. Then, once it is sufficiently cooled down, it slides down the surface due to the increase in density. Therefore, a thermal boundary layer is formed at the upper surface of this inclined cold plate. Now let's look at how air flows at the bottom surface of this plate. Warm air that approaches the bottom surface is still cooled down, thereby causing its density to increase. However, instead of moving parallel to the inclined surface, the denser air will move downward in the direction of its weight. Therefore, there is no opportunity for the thermal boundary layer to form at the bottom surface of the plate. Now let us look at how air moves in the other case wherein a hot surface is placed in a cold environment. At the bottom surface of the hot plate, cold air will slightly move towards the surface, thereby causing its temperature to increase and its density to decrease. This will cause the air particles to rise parallel to the inclination of the plate. Therefore, a thermal boundary layer at the bottom surface of the hot plate. Now let's look at how air moves at the upper surface of the plate. After the cold air moves towards the surface, it becomes lighter due to the increase in its temperature. But instead of sliding up the plate, it will just move vertically upwards because of buoyancy. Therefore, there is no opportunity for a thermal boundary layer to form at the upper surface of a hot inclined plate placed in a cold environment. To compute for the Nusselt number under both cases, we simply use the correlations for vertical plates. However, in solving for the Rayleigh number, we multiply the cosine of the inclination angle theta to the gravitational acceleration g. Finally, it must be noted that the value of the Nusselt number that we will be able to compute from either of these two correlations is only applicable at the side of the inclined surface where a thermal boundary layer forms. Now let us discuss the Nusselt number correlations for flows over horizontal surfaces. It must be noted that the characteristic length for this type of geometry corresponds to the ratio of the surface area A sub s to the perimeter of the surface P. Now, convective heat transfer over horizontal cases may fall under one of four cases. First is when the plate is cooled and its top surface is exposed to hot surroundings. Second is when the plate is hot and its bottom surface is exposed to cold surroundings. Third is when the plate is cold and its bottom surface is exposed to hot surroundings. And the last case is when the plate is hot and its top surface is exposed to cold surroundings. We will analyze in the next slides how air flows in each of the four cases. Let us now analyze how air flows in case 1. Hot air will first approach the cold surface. Then, once the air particles cool down, they will sink at the bottom of the hot air particles, thereby forming this air plume within which air particles are moving due to density difference. Now let us look at how air flows in case 2. Cold air will slightly move towards the hot surface. Then once the air particles heat up, they will then rise at the top of the cold air particles, thereby forming this air plume within which air particles are moving due to density difference. It must be noted that for both cases, no thermal boundary layer was formed at the surface of the plate. The Nusselt number correlation for case 1 and case 2 is given by this formula. It must be noted that this correlation is applicable only for this range of the Rayleigh number. Now let us look at the direction of the convection current in case 3. Hot air will rise first to the cold surface. Then once the air particles cool down, they will sink at the bottom of the hot air particles, thereby forming this air plume within which air particles are moving due to density difference. Now let us look at the direction of the convection current in case 4. Cold air will slightly sink towards the hot surface. Then once the air particles heat up, they will then rise at the top of the cold air particles, thereby forming this air plume within which air particles are moving due to density difference. It must be noted that for both cases, no thermal boundary layer was formed at the surface of the plate. There are two Nusselt number correlations applicable for these two cases. When the Rayleigh number lies between 10 to the 4th and 10 to the 7th, we use this Nusselt number correlation. On the other hand, when the Rayleigh number lies between 10 to the 7th and 10 to the 11th, we use this Nusselt number correlation. Now let's look at how air flows over a long isothermal cylinder. Isothermal horizontal cylinder. Let's assume that we have a hot cylinder placed in a cold environment. In this case, cold air near the cylinder will slightly approach the surface, which will cause it to heat up. This will cause its density to decrease, thereby allowing it to rise above the surrounding cold air. But as the air rises, it also starts to cool down again, therefore assuming this plume of air within which air particles are moving. For long isothermal horizontal cylinders, we use this correlation to compute for the Nusselt number. Take note that this correlation is only applicable for this range of the Nusselt number, of the Rayleigh number rather. For flows over spheres, we use this Nusselt number correlation. Kindly note that this is applicable only for the following ranges of the Rayleigh number and the Prandtl number. In the next video, we will present the correlations to compute for the Nusselt number for flows within parallel plate channels.